Hi guys, this video is about implementing a simple parser, a so-called recursive decent parser, and of course we will use this for our compiler project, but we will begin kind of simple. We will first implement a calculator. Let me first show you in a quick demo what my calculator currently supports and allows you to actually compute. In the video I will show you how to come up with an implementation for that, and then in the exercise you can extend this calculator for additional operations. Currently, the calculator just supports a few integer operations like addition, subtraction, multiplication, division. It takes into account that certain operators have higher precedence than other operators, and you can use parentheses to group sub-expressions. You can use it from the command line. You can just type in certain expressions followed by a semicolon, hit return, then you see the result. Or you can type in a bunch of such expression statements into a file and redirect it, of course, to standard in. Let's start with something simple. I just want to add a few integers, so I type in this expression followed by a semicolon. And you see the result is 19. Let me also show you that the operators are, in this case, all left associative. That means I'm evaluating the expression from left to right. So if I would change this into a subtraction, it will first compute 12 minus 4, which is 8, and then minus 3, which should be 5. And okay, then let's also show you that this is doing integer arithmetic. So this will not give you a fraction, it gives you 1. If you would type in an expression without the semicolon in the end, and you just would hit return, it takes until you actually have the semicolon, which makes it an expression statement. And if you would forget the semicolon, let's type in, for example, 12 plus 4. And then I type in Ctrl D for generating the end of file, which will generate the end of input token, and this will give me an error message here. You also see that you actually have here line numbers in the error messages, even though you're using it interactively. You, of course, can type in the statements into a file, like, for example, a file like this here. And then the line numbers and column numbers, of course, would make more sense in error messages. Now, in this case, I will not get an error message if I redirect the file to standard in. But let's say I change it so that I, for example, forgot here the semicolon in the first line. Then I now get the error message that the token in the second line, in the first column, should be a semicolon instead of this decimal literal. Or let's create another error message. Let's fix this here, but let's say we forgot here the asterisk. Then this is not a valid expression. So of course we have to talk about what grammar is implemented in this calculator. This is the grammar supported by the calculator that you just saw, the production rules describing this grammar. And of course the purpose of this video is to show you how you can come up with your own implementation of such a calculator. And in order to bring you there, showing you how this can be done in a very simple pattern, step by step, I want to simplify this grammar first. And the first simplification will be that we just support one expression statement. So we will kind of begin with that. It will actually not be the first grammar that we will consider. We will simplify it further. Now, compared to what you saw before, we just got rid of this input sequence. We just have one expression statement, but operators are still left associative. This is certainly what we want. Think of this example where we do subtractions. Then you want to have an evaluation from left to right. But I think it's simpler to start with operators that are right associative. So before I show you how to implement a grammar like that in a parser, let's first rewrite this so that this operators for subtraction, addition, multiplication, division are right associative. This simply means that, for example, this production rule for an expression will be rewritten such that basically just this non-terminals for term and expression are replaced, swapped. And also in the production rule for the factor, you just swap these things. The production rule for factors actually will be the same. So this is already kind of final. So this is kind of what we begin with this right associative operators, but keep in mind that we want to have that. Now to show you these clear patterns, how this can be done step by step, I actually will rewrite these rules, these production rules, further in a different notation, which is simpler for translating the formal description of a grammar into an implementation of a parser. This other notation for expressing production rules is called Ebnf, and I will just introduce this notation here in this video by giving you a few examples. And actually what I'm using here is kind of an Ebnf dialect. On the website I can provide you information for a more formal description. First of all, you will see that with Ebnf it's possible to write down a grammar more compact. Like in this example, where I want to express that a non-zero digit consists either of the digit 1 or 2 and so on. I can write that down in just one production rule, in just one line. And that's not due to the fact that we have a few minor modifications in the notation, that these arrows become equal signs and that double quotes are used instead of single quotes for expressing that certain characters belong to a terminal symbol. It's because you have these so-called meta symbols in the Ebnf notation. Like here, this vertical bar is a meta symbol. And it's used here on the right-hand side of a production for a so-called alternation. It's also used in this next rule for expressing that a digit is either the digit 0 or a non-zero digit. And there are other meta symbols. For example, in this rule, I use this meta symbol for a repetition, this curly parenthesis. And with that, I want to express that a decimal literal can consist of just one non-zero digit, but it also can be followed by an arbitrary long list of digits. And for the grammar of the calculator, I will actually require 2 more such meta symbols. So let's rewrite the grammar for our first calculator, where we just have one expression statement and where all the operators are right associative. Rewriting the first rule is simple. We just replace the arrow with an equal sign and the single quotes with double quotes. For the next rule, I actually have to introduce a new meta symbol for a so-called optional group. I want to express here in this rule that an expression can be just a term, but after this term, I optionally could have either a plus sign followed by an expression or a minus sign followed by an expression. And I can write this down even more compact by using this round parenthesis here for grouping things. You have to know that all these meta symbols also are having a certain precedence. And here I want to express that in this optional group, I first have either a plus sign or a minus sign. And after that, I have an expression. So with that, we simply can rewrite the next rule in a similar way like that. And for this last rule, I actually will use more than just one line, because I think it's in this way more readable. You will see that now it would be possible to actually use just a tool for generating a parser from this Ebnf notation of the grammar. That means we could use a tool that uses the Ebnf notation as input and would generate some C program with a parser that simply would check the grammar, whether it's satisfied or not. It wouldn't do some computations. This can be added afterwards to this parser. So that means you would get feedback from this parser like your user input satisfied my grammar, or inline so-and-so, column so-and-so, some semicolon was expected, but some decimal literal was found. Something that you already know from using compilers. Of course, we will not use a tool for generating a parser. We want to understand how such a tool would work internally. You basically can translate this Ebnf notation into an implementation of a parser. And you will see that it's actually kind of simple. You just have to follow simple rules, and by that you will understand how these simple rules could be used to actually write a tool that would do this for you in the future. Of course, such a parser will not process the user input character by character. It will use the lexer that we already have. And we will expect that before you call the parser, this getToken function was called once. That means we have a current token, and with getToken we can consume a current token and get the next token. The rules for coming up with an implementation for the parser are, for example, that for every production rule in this Ebnf notation, you provide one parse function. That means for this expression statements, we would have one parse function, and the naming convention will be parse followed what we have on the left-hand side of the production rule. So basically that parse expression statement. And similarly, there will be parse expression, parse term, parse vector functions. Now for the implementation, you simply have to look what you have on the right-hand side of a production rule. Here we have to check whether the tokens that will be found next satisfy the grammar of an expression. For that, we will simply call the parse expression function. And this parse expression function somehow has to check that. That means either this function simply returns if the grammar is satisfied, and otherwise it will already have terminated the program with some error message that in a certain line with a certain column, a certain token was expected, but some other token was found. So let's assume that this function returns. Then all these tokens for this expression are already consumed by this parse expression function. That means now we just have to check whether the current token is the semicolon token or not. And if this is not the case, we somehow have to print an error message and terminate the program. For that, we will implement one function for doing all this error handling, an expect function. It simply will check whether the current token is a certain token or not. If it's this token that we expect, it simply returns, and otherwise prints this error message and terminates the program. So let's assume that this expect function returns. That means we know that the current token is the semicolon token. That means we just consume this token with getToken, and that's the implementation for this rule. For the next rule, I also want to show you here on the slides how to do the implementation. Here we have to take care of this optional group. So first we check whether we have a valid term. That means we call the parse term function. And then we have to check whether we have this optional group or not. For that, it's here very simple, because if we have this optional group, the current token either is this plus or this minus token. And that means we simply check if the current token is one of these two tokens. If this is the case, we consume this token, and after that we check whether we have an expression by calling parse expression. And then you see here, this is a recursive call in this case, and that's why this parser that we generate will be a so-called recursive decent parser. Decent because it's parsing the grammar top down, and that's why you have this decent, and recursive because the calls are recursive. Now in the demo I will show you how to implement a parser for this grammar from before, and I also will show you how to then add to this parser some functionality so that it's actually doing the computations. This is then a so-called parser with annotations. Basically, I will implement the complete calculator in just one source file. Of course, we already have the source files for the lexer and the source file for token kind, and these headers. I will, of course, use them, but the rest of the calculator just goes into one source file. What you see here is basically the source file from the calculator from before. I just removed all the parse functions and the call of this first parse function in function main. Before I begin with the re-implementation, let me show you how this error handling functions can be used. You already saw this expected function on the slides. So if I use it like there with semicolon, translate this and run this program, and now type in Ctrl D, then the current token will be end of input, and I will get this error message expected semicolon got end of input in line 1, column 1. This other function simply expects a string as parameter. You will later see that ideally we would have a expected one-off function. I will come back to that later. So, but for now, it's sufficient to know that if this function is used, you simply see whatever this string is as the expected token. So here again, I just type in Ctrl D, and then you see now factor instead of semicolon. So no big deal, but I just want to make sure that I now can move this to the top and focus on the implementation of these parse functions. Actually, I will begin with declaring them first, because we have this recursive function calls, and before you can call a function, you have to declare them. So we have parse expression statement. We have also parse expression. Then we also have parse term. And we also have vector. And then in function main, I do here the function call of this parse expression statement function. And then I actually begin with the implementation of parse expression statement. Maybe I simply copy paste this here, change this here from a declaration into an implementation like that. And then I first have to check whether we have a expression by calling parse expression. Then I have to check whether after that the current token is the semicolon. If this is the case, I have to consume this current token and get the next token. Then I can implement this parse expression function. Here I first have to check whether I have a term by calling parse term. Then I have to check whether this optional group is there or not by checking whether the current token is the plus token or the minus token. So if token kind, this is this global variable for the current token, is plus, or token kind is minus, then we have this optional group. That means first we have to consume this current token, and then I have to parse an expression. Okay, so that's it. Now, the implementation for parse term, you will see, will basically be the same. I just have to replace a few things. Here I first have to parse a factor. After that, I have to check whether the current token is a token for the multiplication, the asterisk, or for the division, the slash. So if token kind equals the asterisk, or token kind equals slash, then we have this optional group. So that means, again, I first consume this current token, and then I have to parse another term. Okay, so that's it for parse term. And the last parse function, parse factor, now first checks whether we have one of these different literals, decimal literal, hexadecimal literal, octal literal, or this open parenthesis. So if token kind is a decimal literal, if this is not the case, we have to check for a hexadecimal literal, maybe next. After that, for an octal literal. After that, for this open parenthesis, an L parenthesis, and otherwise we have an error. And here I need this expected error function. And here it would be nice to have an expected one-off function, specify this list of tokens above that are actually expected. So here I just say I expected some factor, and from the manual it has to be clear that this means one of these 4 tokens was expected. Now if we actually have a decimal literal, it just means that we consume this token. And then we can return from this parse function. And the same will be the case here and here. If we have this open parenthesis, then we have to consume this. After that, we have to parse an expression. So we call it parse expression. After that, we expect this closed parenthesis, an R paren. That means we have another call of expected. And after that, we consume this. Okay. Now let's try to compile this. So this worked. Now let's test it. Let's begin with some expression that is correct, something like that. Again, it will, of course, not compute anything. It will just check the grammar. Now I type in Ctrl D, and I do not get an error message at least, and this means the grammar is okay. Let's try something where the grammar is not satisfied, something like that. Then you get here in line 1, column 6, so this would be 1, 2, 3, 4, 5, 6. So this plus is causing this error message. Here a factor is expected, but a plus was found. And actually, I think in this form, something like that also would be accepted. But that's actually violating the grammar. In our current calculator, we just allow one expression statement. So let's fix it for now, just like that. After this expression statement was passed, we expect the end of input. Okay, now again. Now we get an error for that. Now before we add some more functionality to this calculator, so that it's actually computing something, we should somehow see this call stack, the parse tree generated by this parser. And for that I will simply add a function that prints a certain string with a certain indent. This function will go somewhere here to the top with all the other debugging functions that we might come up with. And it will be called print with indent. It receives as first parameter the indent and as second parameter a string. And for printing the indent, I simply use a for loop like that. I initialize I with 0. I should be smaller than the indent times 4. And in the for loop body, I simply print a space. So very simple implementation. And after this indent, I print the string. And then you can use it like that. Let's do this here. For example, with an indent of 0, I want to print here. And maybe I also should print after that a new line. After the string. So I want to print first here with an indent of 0, then maybe with an indent of 1 now there, and then again with an indent of 0 back, something like that. And then you can have things like that. Okay, now I simply insert this in each function as the first argument. This of course means that I have to change the signature of the functions. They should receive an indent, and with that indent they print the name of the function. And similar here. And also here. So this is parse expression. And maybe also here, although it's not necessary because this function only gets called once. And then I also have to change this forward declarations. So they at least should have the type of the parameter. And of course, all these function calls of these parse functions. And they will get as parameter always the indent +1. Actually, you're not here. I have the indent of 0. Okay, and now we should see the call tree. Let's use an expression like 12 plus 4 plus 3 semicolon, and then you see how these functions call each other. And maybe we also should print, at least for the parse factor function, what token finally was found for the factor. So we could simply do the following. Here I print, for example, the string representation of the decimal literal. So that means I simply print token val C string. And the same I will do here and also here. And maybe I also print this token for the open parenthesis, the string representation for the token using this string token kind function for the current token for token dot kind. I also can do this for the closed parenthesis here. And maybe it's also a good idea to print what kind of operator we found in this optional group. So I simply paste this also to here and to here. And yeah, that's it. With that, it should be now more readable what we see when we run the parser. Now let's see what this output of the parser will tell us. Let's use an expression with 3 plus 2 plus 1. If I get it managed, you now will see on the left-hand side a tree representation for this expression. But it's important to see that you actually can get from this output generated by the parser basically this description of this expression as a tree, as you hopefully see on the left. You see here that parse expression statement was calling parse expression because the indent is increased by 1. And this parse expression function generated this root node with the plus sign. And in general, you will see that if such a tree representation has a plus or a minus node, this was always generated by parse expression. And these nodes, of course, have always two children, a left child and a right child. The left child, in this case, was generated because parse term was called, which called parse factor, which then found this token for this decimal literal with value 3. Then parse factor returned back to parse term. Parse term simply returned to parse expression. And then this plus token was found. That meant that we called another time parse expression, which then generates this right child of this node. And here things just repeat. We again have a left child generated from this call of parse term, which called parse factor, which found this decimal literal with value 2. Then this function returned back to parse expression. Then this plus was found. And then this right child was generated from calling another time parse expression, which simply called parse term. Again, parse factor. This found the decimal literal with value 1. Then this functions return to parse expression. This time no token for this optional group was found. The optional group was here empty. So that meant here we just generate one node with this decimal literal 1. And that's why we have this tree representation as it is. Now let's terminate this program with Ctrl D. And let's change this print with indent function as follows. I just want to have this output in debug mode. That means I use here some preprocessor directive. If not defined ndebug, then this should be actually done, and otherwise the function body should be empty. Okay, now you will see if I compile this with the preprocessor options. So specify here CPP flags -d ndebug. Then this output is gone if I call the calculator again. And if I recompile it, for that I have to touch the source file, otherwise make will say nothing to be done. Without this option, we have them back. Okay, and now we can think about how to add some functionality to the calculator so that it's actually worth being called a calculator. And for that I will change the declaration for most of these parse functions. Passing an expression and passing a term and passing a factor will now return an unsigned integer, the value of the passed expression node. So for that I will use the type unsigned integer with 64 bits, declared in standard def.h. So I have to include this, of course, also. And in parse expression statement, I will now simply print what value was returned by parse expression. So I will first print here this prompt. Then I want to print an unsigned integer with 64 bits. For that, I will use this macro defined in int types. Print unsigned integer with 64 bits. And after that, a new line. So what I have to include is for this type unsigned integer 64 bits, the header file standard def, and for this macro, the int types header file. And here I see that this int types is kind of a leftover from my original implementation of the calculator. So this is already there, but standard def is still missing. So we need that. And now I have to change, of course, the signatures for all of these parse functions, for these other parse functions, and also the implementation. So this now returns an unsigned integer. And the idea will be the following. The value of this passed expression node is the value of this passed term node. So I will store the return value of passed term in some local variable val. And if the optional group is empty, then this will be simply the return value. So I will have here in the end return val. However, if this optional group is not empty, then I have to update this value by either adding or subtracting the value of this passed expression node here. So what I have to do is I first have to remember what kind of operator we found before I forget it with this getToken call. So I will store this operator in a local variable of type enum token kind. I call this local variable op, and this is just the current token kind. Then I forget the current token, I get the next token, then I pass the expression, and the result of that will be stored in another local variable of type unsigned integer 64-bit. And this will be called val write. And then depending on whether I have an operation for adding or subtracting, I update val with val right by either adding or subtracting it. So if the operation was a plus, then val becomes val plus val right. And otherwise we just have these two cases, so I simply can use a else, otherwise I subtract it. And basically in a similar way I will now change parse term. So also first return type, then I store the return value from this into a variable val. This will become the return value, and depending on whether we have an optional group and what kind of operator we have, I will update this value. So here I also use the same name for the local variable val right. This is what value was found in this parse term function call, in this parse, in this term node. And if the operation was a multiplication, then value becomes updated by val times val right. And otherwise I do an integer division. Okay, and now we just have one more parse function for parsing a factor. And if we find here a literal, a decimal or hexadecimal or octaliteral, we have to convert this string representation of this literal into its numerical value. Now in this demo I will simply use a function from the standard library for converting a string into an unsigned long variable. The function is called string to unsigned long. The first parameter is the address of the first character of the string, so that's token val.cstring. Then there is an optional variable parameter which can be used to get a pointer to the first invalid character in this string representation, which I will not use, so that's why I pass here a null pointer. And then I can specify here the base, and for literals this actually should be 10. And with that I get a value back, and this will be basically the value that I will return. So here I also of course should change first the return type to unsigned int 64 bits. I will have here a local variable that I will 0 initialize first, val, and this call of string to unsigned long will actually set this value, and this also will be then returned. And like that I can convert this string into a numerical value. Here I have to specify this base 16, and then I also use it here for getting the value of this octal representation. So here the base should be 8. If we have a open parenthesis, then the value will be what we get back from parse expression. And so here I will return this. And otherwise, if we have this expected error function call, the program anyway would terminate. But if we do not have a return statement here, we would get a warning from the compiler. So let's return something. Actually, I could return val, and I will leave here a comment that this actually never will be reached. Now for this function for converting a string into an unsigned long, I also have to include standard lib. It's already here, so this is probably also a leftover from my original implementation. No, actually I required that for this exit function. Okay, but now this should already work. So let's do some computation with our calculator. Let's say we want to compute 3 plus 2 plus 1. And then we see the correct result, 6. Now let me also show you that we do actually have a problem with this current implementation because our operators are not left associative, they are right associative. And you will see problems if you do a subtraction or a division. So let's do a subtraction here. But of course, you also should try now that you can do things like multiplication. You can use parentheses for grouping things. But let me first show you the problem. It's computing here 2. But what we would expect is that first 3 minus 2 gets computed, which gives 1. And from that, 1 gets subtracted. So the result that we would expect if we evaluate this from left to right would be 0. But it's actually computing here first 2 minus 1, which is 1. So this right part, it's doing things from right to left. And this result, 1, gets subtracted from 3. So that's why we see 2. If we would like to have the result that we expect, we have to use parentheses like this. We first want to compute 3 minus 2. And from this result, we want to subtract 1. And now you will also see that the tree structure of this expression changes. And this actually should be the default if we do not use parentheses. Now again, compare this to what we get here. If I use this expression, which will basically be the same as if I would use parentheses here. And of course, try that out, that with or without parentheses, you will get the same tree structure. So the problem with the parser currently is it's using a grammar that you would not expect for parsing an expression. You would expect that these operators are left associative. So what we need to do is we simply have to rewrite the production rules for left associative operators into Ebnf. And you already see how this then looks like. So of course you also can express this in Ebnf. But the problem here is that you also have to come up with an implementation for this parse function. And that means you somehow have to check whether you have this optional group or not. And to check whether you have it, you would first have to call the parse function for this expression first. And this somehow means that you would have a recursive call of this parse function. And this is not easy fixable. And we want to have a simple solution. So what you can do in this case is you simply rewrite this Ebnf notation into a notation that uses these repetitions like that. You first check whether you have a term by calling the parse term function. And after that, you simply check whether there is a plus or minus operator followed by another term. And this repetition will be implemented in a simple while loop like that. Now, in the implementation of the parser for supporting this modified grammar, we just have to modify a few things in parse expression and parse term. Let's begin with parse expression. This if statement now becomes a while statement. So we change this into a loop. And in the loop body, we will not parse an expression, we will parse a term. And that's it for this implementation of parsing an expression. Now, of course, it's also important to understand how this will change how expression nodes will be generated. Let's assume we parse the expression 3 plus 2 plus 1. Then with parse term, we first get the value 3. Then after that, we find the token plus. That means we enter the loop. Then we parse the next term, which will give us the value 2. From this, we will generate a node, a plus node, where the left child is 3 and the right child is 2. Then, after updating the value, we check again whether we should re-enter the loop. We will have to re-enter the loop because we find another plus token. And that means we generate a new node. What we found so far will be the left child of this new node. And this next term, the term with value 1, will be the right child. And this will give us the expression tree that we want if we do not use parentheses. Now, of course, we do not actually currently generate these nodes, but these nodes are basically given to us by the core stack. But later you will see we will actually generate a data structure for a tree representation of an expression, and then what I said will be perfectly true. So now let's just complete here the implementation of this parser so that it is now following this new grammar. So we change this also here from an if statement to a while statement, and here we will pass a factor instead of a term. And that's it for this calculator project from my side. In the exercise, you will have to make some additional improvements. So now let's check this. Now let's compute 3 minus 2 minus 1. And yeah, now we get the 0. Oh, but actually I still have to do something because I promised you that I will show you how to come up with my initial implementation of the calculator, and you see we still have this limitation that just one expression statement can be passed. But I guess you already would know how to improve that. We will have a new parse function for this actual rule that I should first rewrite into Ebnf, a parse function for parsing an input sequence. So let's also declare this here, and I will call this parse input sequence. And yeah, you also could use here a parameter for the indent, and I just can copy this here. So this is now parse input sequence, and it simply calls parse expression statement until the current token is the end of input. Then I also can remove this expected end of input in function main. So this simply will be a while loop while the current token kind is not end of input. We call parse expression statement. And this gets indent plus 1 as parameter. And that's it for this parse function. Then in function main, I can remove this expected function call. And this is now parse input sequence. Okay, but this is now really it for me in this video. Now let's just check if this is actually working. So this is the first expression statement, and this, for example, the second. And with Ctrl D, I can terminate the program. That's it for this video. On the website, you will find an exercise for improving our calculator. Basically, it's about supporting additional operators. For these additional operators, I will provide you the extended grammar in Ebnf form in a way that you easily can implement the parser. And you will see that these new operators will be right associative. So it wasn't a complete waste of time to show you first how to implement right associative operators. And I will also provide you information for the more theoretical background of this topic.